will start
Yes,
now.
yes, ma'am. Yes, done. Started recording. Recording has started.
Okay.
Yes, we can able to see the screen, sir.
Now you're able to see my screen. I'm sharing my screen.
Yes.
Yes, sir, it's
Yes.
visible.
Is visible well?
Yes.
The folder is visible.
So please allow me to start, ma'am. Then I will start.
You start. Your presentation is not open till now.
So I should start now.
You can
Uh,
start. Time start. Time is 10 a.m.
Ma'am, can I introduce sir to the audience?
But you just start your presentation. Means the slide should come. Vivekanand sir,
Yes,
your
ma'am.
slide is not coming.
Slide is not coming. I'm sharing.
Your folder is visible, sir. Expert lecture, but there you open the presentation. PPT you can open, sir.
You open your
Open.
presentation.
I'm opening, sir, and this is now open the slides.
And then you just minimize that folder, sir. I think it just minimize the folder.
Share has window.
Yeah.
Otherwise, you give your presentation. Our organizer will move.
I'm trying, ma'am. Just for a
Asha,
moment.
can you move there? You are there for 1 hour.
1 hour I'm not there, ma'am.
Huh?
Next hour I'm not here.
Just 1 hour.
Okay.
Vivekanand sir, there one arrow is there na after mic share.
Uh,
First you open your presentation, then minimize it.
Share the entire screen.
okay now.
Yeah, nice. We are
Yes.
coming, sir.
It's visible, sir. Visible.
Slideshow. F5.
Okay. We'll go ahead now. We'll start now, ma'am.
F5.
Yeah.
F5 main.
Yes, sir.
Now
Yes.
formal way of your introduction will happen. Then you can start.
Okay.
Okay, Asha madam,
Yes, ma'am.
you start
Record started.
recording and somebody should take the screenshot.
Yeah, yes, ma'am.
Okay.
Good morning, one and all. Welcome to the sixth day of 15-day faculty development program. Today's speaker is Dr. Vivekanand Mishra. On behalf of Oxford College of Engineering, I'm very happy to welcome Dr. Mishra. Vivekanand Mishra received PhD degree from IIT JSU. We have more than 22 years of experience in education, research, student mentorship at national and international level. He has guided 8 PhD students. 4 are pursuing and executed government international agency funded projects. He is a senior member of IEEE, fellow member of IETE, member of IPS. He has published more than 100 papers in peer-reviewed journals and published and presented more than 90 conference papers, published 3 books, granted 3 patents with 1 copyright, and he has delivered projects for prestigious funding agencies across the world as lead investigator like eScience Malaysia, DST, and DRDO India. Dr. Mishra is also working with many Malaysian universities as collaborator in collaborative projects. At present, Dr. Mishra working in Department of Science, Alliance University, Bangalore, India as professor. Dr. Mishra has more than 2 decades of academic experience in institutions across India and abroad. He is involved as project leader, investigator for various projects funded by the DST, DRDO, India and Ministry of Science and Technology, eScience, MOSTY, Government of Malaysia. Dr. Mishra was active member and secretary of High Speed Broadband Network and chairman of Optical Communication Group OGC at Multimedia University and UTAR, Malaysia. Dr. Mishra's research interests include optical fiber communications, optoelectronics devices, nonlinear optics, optical sensors, optical amplifier, antenna, and metamaterials. So, join me welcoming Dr. Mishra to today's session. Welcome over to you, sir.
Thank you very much, ma'am, for the nice introduction. Okay, so
Welcome.
let's we start the topic of discussion. Uh, the topic of discussion, what I'm going to introduce to the audience today, long, ultra long period optical fiber grating and its application. But, there is a tremendous growth which has been noticed in the last few decades in the field of fiber optics communication. Because of unique property, especially the huge bandwidth, electrical immune, higher secure information. These are the reason the optical fiber communication, well stabilized technology in today's scenario. But the main problem in the optical fiber communication is controlling the light. How to control the light if light is coming in or out, how to filter. We have bulk devices with higher loss, very difficult to align with laser, with optical fiber. Because if you're talking about optical fiber communication, you're talking about the in micrometer in scale, here like thin structure. So it's very difficult to align the big components because of the huge size and all. So it will be interesting if the components with very, very minimum loss, higher stability, small size, low cost. If such type of optical fiber components are available, it will be easy to communicate. So in this respect, so many components are there. One of the very common component and very important component in today's optical fiber scenario, in optical fiber communication, in optical fiber sensor, one of the component is the fiber brake grating. So you can see this is the fiber brake grating structure flashback. It started especially first time in 1978. Just Hill and his co-friends had the first time write grating inside the optical fiber. Then holography technique has come in 1989. And but main work which has been done, tremendous work has been claimed by the Wenckerker once he presented first long period grating in 1996. As we know that we have two types of the fiber grating and long period fiber grating. Here myself and my group, we are working in the field of the long period grating, where the gratings will make in millimeter to 100 millimeter in range. Not only the long period grating, but some of my PhD students and some of the researchers, they have worked on the ultra long period grating. If the grating period is going to be more than 100 millimeter, so we'll know that why the ultra long period gratings come in use and what is the reason behind this. Okay, so there is a lot of applications. If we're talking about the hyperbaric grating, a lot of applications are there in terms of the temperature measurement, in terms of the strain, in terms of the index of the refraction sensing. A lot of applications are there. Just by changing the slightly the refractive index, and we can get the change of the the external perturbation. So these are the reason we go towards much more the hyperbaric grating, especially for the sensing. So if you're going for the long period grating, so long period fiber grating, the main property of that one is the coupling efficiency. Coupling of the fundamental mode, the core mode, with coupling with towards the same direction cladding mode. If the coupling will take place, core and cladding modes, and then we can get the coupling wavelength, and then that loss which one we get, that one is totally depend upon the coupling of the modes. The absorption loss will take place due to the coupling of the modes, and that absorption of the loss which will take place in the fiber long period fiber grating, that one will be mode selective, because specific mode is going to be coupled in between. It's more selective coupling will take place and that's why space link coupling modes we can get at the output. And that space link coupling modes will let you know all the information if you're using as a sensor, using a long period fiber grating as a sensor. So this resonance wavelength is the coupling of the core and cladding modes which will be taken. And that resonance wavelength depend upon the how much is the effective refractive index core and cladding here is an effective, and the period, of course, period of the long period grating, as I told you, it will in few millimeters, that will play an important role. So if we see the coupling of the wavelength depend upon the period and the change of the refractive index core and cladding medium. So these two are the responsible for this coupling of the wavelength, or we can say resonance wavelength, or we can say loss of the absorption. And based on this only, we are able to work as a long period grating for the sensing purpose. So this is what's happening in the long period grating. You can see here, this is the long period grating. How come this is the core region, this is the clad region, optical fiber. You can see that this is the core region. Light is coming in the core region. These are the fundamental modes. You can see these are the fundamental modes. And you can see this is the cladding modes, which is the higher order modes. So coupling will take place with m is equal to 0, the modes of the m is equal to 0, m is equal to -1. Or we can say the coupling will take place core and cladding modes here. And here you can see there is a circle is showing, one is the hollow circle, one is the solid circle. So here this solid circle is in fact showing the core mode, and this hollow circle is showing the clad mode. And after coupling, you can see you are able to get a propagation characteristics beta at the output. So this is what's happening in the long period fiber grating. Here we can calculate the resonant wavelength just by the refractive index of core minus refractive index of cladding multiplied by the periods of the grating what we fabricated. So this is how we can get the propagation characteristics of the long period grating once the modes are propagating from core to cladding. So we have especially two types of the gratings. One is the long period grating, one is the fiber break grating. So you can see that this is the fiber break grating, this is the long period grating, long period fiber break grating. Here, the fiber break grating, there is a reflectance. This is known as the reflectance grating. Only core modes will change and get reflected. If the modes of the mode and these periods will match together, then it will be getting to be reflected. So of course, this is also a selective reflectance, but this is the reflectance. So fiber break grating, only change will take place from core to core only. But if you're going for the long period grating, you can see that not only the core region, but also the clad region modes is going to be affected, going to be coupled together, and then we are able to get the transmission. So in the long period grating, this is transmittance grating, and fiber period grating, this is the reflectance grating. Of course, if you're talking about the long period grating, then here both core and cladding both are involved here. That's why the effective refractive index is depend upon difference of core and cladding mode. You can see that delta N effective is equal to N core effective minus N clad effective. Of course, period. The period will also going to be one of the portion which will affect the resonant wavelength in the long period grating. But if you're talking about the fiber break grating, you can see here only core refractive index difference we need to be clear here with the periods of this one. Then we can get the resonance wavelength for the fiber break grating. Generally prefer the long period grating is preferred over fiber break grating because there is an interaction will take place from the core region, from the clad region. See, light is hitting the clad region. So due to the hitting of the light at the clad region will give you much more accuracy. If anything which has been kept on the surface of the clad region, then we can get the information of that amount at the output. So due to this region, the long period grating is much more preferred in terms of the sensing purpose compared to the fiber grating. So we can see here the selective wavelength transmittance and losses. You can see the selective loss, absorption loss. You can see here, and this selective loss depend upon
Hello?
the yes.
Yes, sir. Actually, I want to ask one question, sir,
Yeah.
related to the previous slide, sir. So actually, uh, My name is Anand, and I am interested in this fiber grating sensors. So actually, I have read basic study on FBG, but not able to read the long period grating. So my
Okay.
question is that related to grating period. So at which grating period we can differentiate fiber break grating and long period grating. Suppose there is a value, suppose 10,
Yeah,
25 mm or 30 mm. So is
yeah,
there any value that above this is the LPG and below this is the
yeah, right. If you're going for the fiber break rating, then the periods will be in micrometer in range. But if you're going for the long period grading, then it will be in millimeter in range. Sometimes it's going in 100 millimeter. So
Mhm.
it's not exactly fixed amount, but a range we can
Suppose
say.
unit is same in millimeter for both
Yeah,
FBG and so at
correct.
which millimeter range FBG lies and what is the range for LPG in millimeters?
Till 10 micrometer to 1 millimeter if you're going, then it will be fiber break rating. And going 1 millimeter to 100 millimeter, then it will be long period rating. And
One
also,
millimeter.
yeah, also we go for the ultra long, which is going to be more than 100 millimeter as well. So I will show you in the next few slides how the long period grating is going to be more than, sometimes it's going to be 100 millimeter to 1000 millimeter. That one is also in the property of the ultra long period grating. But if you're talking about the fiber break grating, it's not more than the 10 micrometer. It will be in that range only.
Okay, sir.
Okay, Anand? The spectral range of the long period fiber variability, you can see, is highly selective range are there. Specific range of the wavelength is get rejected. These are the rejection bands, you can see. These are the rejection bands, and these has only the transmission band. So rejection band depend upon the specific coupling of the wavelength. Which wavelength is coupled with core and with a cladding mode, that wavelength is a specific wavelength. Not all the wavelengths is going to be coupled together. So the specific wavelength coupling will let us know which band is going to be rejection and which band is going to be for the transmission purpose. So this is the number of rejection band we can see centered at the resonance wavelength, which is 1500. You can see this is a resonance wavelength 1500. And LP01 mode means the fundamental modes, which is generally propagating in the core region, coupled with higher order modes, or we can say the clad modes, and then such type of the rejection modes, which has been gathered with centered at the resonance wavelength at 1500 nanometer. So this is the transmission. You can see the transmission. These are the less transmission, very less transmission, less, the highest less transmission, because of the, these are the rejection only. So these modes are not supporting for the transmission purpose, and not supporting for the transmission means it's going to the rejection band. So this is the unique property of the long period grating, to reject specific wavelength and allow to transmit specific wavelength, and it's totally depend how come coupling will take place between core and cladding modes, or we can say LP01, HE11. So many modes are there, and totally it depend upon the mode coupling for rejection and for the transmission in the long period grating. You can see here more specific the in terms of the linear polarized mode 1, linear polarized mode 2, linear polarized mode 03. You know, this is the fundamental modes, the modes which is propagating inside the core region only. So it's very specific this. So these are the rejection, and this rejection, this specific fundamental order modes depend upon the grating. You can see here. This is the first paper published by the A.M. Mansur, Journal of Light Wave Technology, and this paper is very much useful. We can see the backbone to understand the concept of the long period fiber grating. You can see here how come this grating period is the grating period towards x-axis and wavelength towards y-axis. How come this grating period is responsible for LP01, LP02, LP03? This grating period play an important role for the rejection of this higher order, sorry, the fundamental modes. And this is the mode coupling, what's happening in the long period fiber grating. This is the reference I have taken from the one of the very famous paper, A.M. Mansur. So now we'll move to the next grating, which is the ultra long period fiber grating. As I told you, if you're going more than 1 millimeter, sometimes it's going 100 millimeter, the periods, and then it's become an ultra long period grating. This is the new work which my PhD students have completed, and we got a very good publication on this ultra long period fiber grating, because it's much more sensitive, higher accuracy, especially if you're talking about the for the biosensor purpose. So such long period gratings, especially for the antigen, antibacteria, if you want to go, and which is the bigger insects, if you want to detect, as sometimes some of the insect will spoil the food, and if you want to detect that what are the insects there, then such type of the fiber grating, ultra long fiber grating will be very much useful. Everything is the same, slightly different will be the order. You can see this is the same. The lambda BR, the phase matching condition, or we can say broad wavelength, of course, it depends upon the difference of core and cladding mode, because same concept as the long period grating multiplied by the period divided by n. Divided by n. This n is in fact known as a deflection order. And this deflection order, first order deflection order of wavelength operating B with period, suppose is 350 micrometer, will be same as the second order deflection wavelength operating period with 700 micrometer. So this n play an important role. So this n is the diffraction order. If you dividing with the same phase matching condition of the long period grating, then this become a ultra long period grating, and then we'll see that how the diffraction order will affect the phase matching condition. You can see here how the phase matching will take place with different order. Once the grating length is increasing, see here, the grating length is here, x-axis is 200 to 1600 nanometer, micrometer, and y-axis is showing the resonant wavelength. So if the grating period is increasing, now it's going to be 500 micrometer to 3500 micrometer. Now coupling will take place, you can see here with the LP01, LP00, LP02, this coupling will take place. And this coupling will tell you all the information of the resonant wavelength, all the information for the sensing purpose. That's why I told that long period grating, if grating length will increase, then the first, second, third, fourth order of diffraction will affect a lot your output, and that output will tell you all the information about the coupling efficiency. So it's just about long period grating, ultra long period grating, and all just definition and the working principle. Now we did some mathematical modeling of long period grating. So for that purpose, we use the couple mode theory. Generally, there is a two. One is the transfer matrix method, and one is couple mode theory. So just if you using the general fiber grating, then we use the transfer matrix method, generally known as a TMM. This is especially for the reflectance. Reflectance means fiber grating, right? So, but here, in my case, here we use the long period grating and ultra long period grating. So here coupling will take place, right? Core and clad mode is going to be coupled together, and due to this coupling, we are able to get the higher efficiency at the output. The transmittance we can get. We can say the prop transmittance lambda. So this is happening because of the coupling. So that's why we need to use the couple mode theory for that. Couple mode theory, and this couple mode theory totally depend on the core and cladding modes, amplitude of core and cladding modes. You can see here there's two equations, one for the core, one for the clad. See, this is for the core, CO core, and CL for the clad. For both equations, we can put different equation, and in here inside got amplitudes of core and cladding. This is the core, this is the core, this is the clad. So amplitude of core and cladding, and based on these two equations, if you solve these two equations, we can get the resonant wavelength. You can see here. And if you get the resonant wavelength, easy to find out the coupling efficiency. See, this is the coupling efficiency. And once we get the coupling efficiency, easy to find out the grating transmittance. See, this is the transmittance. This is what we are looking for. This is what the output of the fiber, long period fiber grating. So this is another way to do the modeling of the long period grating, just by using the couple mode theory. And using the couple mode theory, we can get the transmission characteristics of the grating, and we can plot the graph for that different length of reflectivity you can see, and different transmittance and the rejection bands we can get. So if you see all these four figures A, B, C, D, the E is length of the grating for the long period. Length of the grating is 50 millimeter. You can see 50 millimeter. Then you can see that rejection band is wider. Right? This is the transmission. This is the wavelength. This is the rejection band. It's so much wider. So once the length is going to be increased, see now it's going to be 200 millimeter. The rejection band is going to be thinner. Now the length of the grating is going to be 500 millimeter. See, rejection band is going to be very much narrow. Now the grating period is going to be 1000 millimeter. Very sharp rejection band we can get. And how much sharper it will be, more accurate output we can get. Okay, more information we can transmit, right? So this is the effect of the effect of length on reflectivity, we can say, or rejection we can say, by using the long period fiber grating with different lengths. Okay, next new work what we did, and this work also got published in the Optic Journal, Germany. And here we did some novelty. Of course, we got to know what is the long period grating, what is the fiber grating, what is the ultra long period grating. So why not we cascading two long period grating together and we'll check what's happening. We taken the reference of this paper. We taken the reference of this paper and we did some new work. You can see here, there is two long period grating. This is one long period grating, this is another long period grating. And now light is coming from the core region. This is the core, this is the clay. The length of the long period grating is capital L, and the distance from the center of the long period grating of the first one to distance of the center of the long period grating of the second one is capital D. So you can see once light is coming here, coupled in the cladding of the first LPG. See, coupling will take place here. Now transmitting. Now again coming and recouple here, the second LPG, recoupling here. So two times coupling will take place, means here we are getting the interference with light propagation core producing interference fringes with the attenuation band. More accuracy we can get just by multiple times of the coupling will take place from core and clad, or we can say in this case two times coupling will take place core and cladding, and then we are able to get transmittance the lambda, or we can say that absorption band here. So now you can see this is the absorption band for two cascading of the long period grating, which is the big range we can get like that. Okay, so this is the what we got to know about the cascading of the long period grating. A lot of work has been done. This is just I'm showing you one of the work which we did with my group of the PhD students. Okay, so there are several ways, as we know that we can fabricate the long period grating. We can fabricate the grating by the permanent grating, which is not removable. Once it will be made, the grating it will be always there. And second is the reversible grating. So we have two types of the way to fabricate the long period grating. So many technologies are there. One of the very famous technology is face mask technique. You can see the ultraviolet light is coming on this face mask, and then interference will take place. See here, the constructive interference. Constructive interference means all the light signal which is coming here will meet at the face, and due to the constructive interference, it will change the refractive index of this portion. Okay, so moving that, there is a variation of the refractive index, and this is one of the way to fabricate the long period grating known as face mask technology. Second is point by point technique. You can see here, light is incident each and every point on the fiber. This is a fiber holder. I hold the fiber. Now light is coming here from laser beam and incident here, changing the refractive index here. There is, in fact, is very precise motor is there, who is translation from one place to other place, and slightly moving, very slightly moving, left to right, right to left, and we can make the change the refractive index, and the variation of the refractive index, or we can say periodic refractive index variation, is known as the grating. So this is the way how we can fabricate the grating just by point technique, means one by one point we have to change the refractive index. In fact, what's happening in such condition, like interference of the light will take place for the UV light, point by point technique, light will incident on the core region, the there is a variation of the refractive index periodically. This is happening. You can see that step by step what's happening once the UV light will incident on the optical fiber. You can see, especially core region. This is the non-uniform light. Then photoionization will take place once light will incident. Now see, this is the diffusion. Diffusion. Now the silica atoms got diffused one place to other place. Diffusion will take place. Recombination at trap will take place. Now due to that reason, electric field will be produced inside. Refractive index, you can see the refractive index variation will take place. This is the way what's happening in point to point and ultraviolet radiation. Especially the undoped silica is not photosensitive if we using the light signal at 244 nanometer. So totally the change of the refractive index depend upon the irradiation condition, depend upon the intensity, the wavelength, so many factors are there, and this is the way how come there is a the diffusion of the silica atoms will take place, and due to that diffusion, the refractive index is going to be changed periodically, and the formation of the grating will take place. See, this is the non-photosensitive method. Here, this is the optical fiber. You can see carbon dioxide laser will incident. So it will, the place where it will incident, deformation will take place. Like this here, you can see deformation will take place. Deformation will take place, and this deformation will take place means there is a core index variation of the refractive index will take place. This is a systematic diagram for the physical deformation of core index variation just by using the carbon dioxide laser. But the main thing is here, the deformation will take, physical deformation of the core region of the optical fiber will take place like that. And deformation means there is a diffusion of the silica atoms, and diffusion of silica atoms for one place to other place means variation of the refractive index, or we can say that periodic refractive index variation, or we can say that is the fiber grating. So this is another way, just by using known photosensitive method for the fabrication of the fiber grating. Another way you can see the fusion splicer. See here, this is the physical deformation. Same thing by just electric arc method. Electric arc will incident on the fiber core. You can see here, somewhere here. So if electric arc will incident here, then the silica atoms here is going to be diffused, and this diffusion of the silica atoms means change of the refractive index are there, and this is another way to fabricate the grating. You can see the OSA. We can see at the optical spectrum analyzer that there is a change of the refractive index variation will be here. So this is what's happening. The physical deformation just by electric arc will incident, and due to the arc incident, there is a diffusion will take place, and diffusion will take place means variation of the refractive index will take place. This is the fusion splicer, electric arc fusion splicer. See here, this is the fiber. You can see this fiber have removed the core region. Remove the gliding region. Only core region is here, and somewhere it's going to be touched together, and then just one click, electric arc will incident on this portion, and electric arc will incident means changing the refractive index. So it's very precise. Controlling parameters are given here. It's not specific arc current supposed to be there. Electrode wire should be there, and number of periods 15 to 100 we can fabricate just by using such type of the method. So many methods are there for the fabrication of the grating, and not only this. After fabricating the electric arc method, the fiber grating, we can calculate the refractive index how much has been increased just by using this specific formulas for the germanium diffusion coefficient, diffusion length. Using this formula, we can plot the graph between the refractive index and degree of centigrade. So you can see that there is a fictive temperature around 1500. 1500, you can see there is a specific refractive index will increasing. See, refractive index is increasing very fast to 1500 centigrade. After that, it's decreasing. The temperature at which the refractive index start decreasing, that temperature is known as the fictive temperature. In this case, is coming around 1500 degrees centigrade, and this is very much useful for the geometrical deformation, change in glass structure. So this is the this mechanism is useful, or we can say electric arc method is a lot of application in terms of the deformation of the optical fiber. These are the reversible grating. Till now what we are discussing, that was not reversible, but this is the reversible. Once you apply the pressure on the grating, sorry, on the optical fiber, then grating will form, and if you remove the pressure, then it will come in the original shape. So this is what's happening. You can see this is the optical fiber, and these are the groove plate. Groove plate have been kept on the surface of the optical fiber, and bottom is the flat plate. Okay. Now pressure has been applied from the groove plate. So what will happen? The place where sharp region is there, sharp region, the groove plate sharper region will apply more pressure. So means that particular region, the refracting index will change here. So refracting index will change here. And once you remove the groove, then it will come in the original shape. So this is the reversible grating formation technology. Not only this, another way you can see that graphite rod are there, and also same procedure, just apply the pressure. In between, this is the optical fiber. You can see this is the optical fiber. Graphite rod are there. Just apply the pressure on the surface, and just by applying the pressure, the place where the rods are connecting, sharply on the optical fiber, that place refracting index will change. Okay, this is another way. You can see in this method here, this is just winding the wire around the fiber. See, this is the optical fiber, and wire has been winding towards the optical fiber. See, this is one. Wire is surrounded around the optical fiber here. Okay, and this is the pulley. The pulley is pulled down with 100-gram weight. See, once applying the pressure here, down, then this pulley will very tight, and the place where it tightened region is there in optical fiber, the refractive index will change, or we can get fiber break grating. So these are the reversible method for the fabricating of the fiber break grating. With different ways are there. So I've taken the reference of some of the scientists who have published this work in the very good journal, like Savin and co-workers published such reversible grating formation techniques in the optics later. Sohn and Song have published such type of the fabrication in optics communication paper. C.D. Paul and co-workers have published same reversible grating in Journal of Light Wave Technology, because these are very much useful, especially in the terms of the optical sensor part. Especially if you're talking about, suppose you are coming with a device, fiber grating a device, and for the optical sensor purpose. So the when you need as a sensor, that time you apply such technology and use that. And if you don't want, just remove the technology, then it will come as a simple optical fiber. So this is the reason it's very much useful. A lot of work has been done in the field of reversible fiber grating. You can see that same how to measure that, the property of such type of the fiber. See, is the broadband laser source, and this is the weight has been kept on the surface of the fiber. Groove plates are there, and different groove plates, different range of the periods groove plate, different spectrum you can see at the output. So this is the optical spectrum analyzer, where we can see that different the spectrum analysis we can do just by different weight, not only different weight, but also different periods of this groove plates plate. So weight and periods will modulate this spectrum analysis here. Same thing is here. You can see optical spectrum analysis showing the transmission spectra of long period grating. Also, same thing, you can measurement output spectrum by SLED. The fiber cleaving machine, splicer. Before doing all this, we need to cleave the fiber. We have to remove the jacket. We have to remove the clad region. Then core region only you have to insert from both the sides. Okay. So in my case, myself and my team has taken the single mode fiber 28, and then jacket removal just using the JR25. Cladding portion has been removed by the stripper. Fiber protective sleeve inserted. Okay, after this there is a sleeve is there, then you have to insert the sleeve, and fiber cleaned with wipes of the isopropanol, fiber in prepared using the fiber cleaver. Okay, and then after electric arc will incident, and splicing will take place inside the fiber. fiber splicer machine where the splicing will take place. Not only the splicing will take place, so many applications are there. Using this, we have fabricated the fiber by grating also, just by very precise motor, just by moving the fiber, and arc will incident in each and every point of the fiber, then the refractive index will vary. So this is splicer not only to joining the fiber, but also very much useful for the grating, for the fabrication of the grating purpose. Okay, now once we see, this is our setup. You can see this is the fiber grating here, and we apply the weight on that, and different weight we can get different output here. Okay, and our intention is to find out the power. See here, we got the power. With here we can convert it to power. So we can see the power loss with different wavelength. We can get it. So in this case, transmission characteristics we got for the long period fiber rating in single mode fiber, and we can convert the power just by converting the mass to power, and based on that we can get the resonant loss peak is around coming 7 decibel. So a lot of applications are there. Not only that, band rejection filter is very much useful in optical fiber communication purpose, where resonance wavelength can be tuned by changing the period of the blue plate. So according to the requirement, you can reject the signal just by changing the period of the blue plate. You can make unique type of the, according to your requirement, you can make the band rejection filter. So this is one of the application of the long period fiber grating and ultra long period fiber grating. Multi-channel filter we can use with cascading of so many long period grating together. We can use as a pressure sensor, fuel adulteration sensor. A lot of applications are there using such type of the fiber grating. You can see here the band rejection filter, how can we use with different power and wavelength. You can see that. So you can see this one is 600 micrometer, 1200 micrometer, 1800 micrometer. This is the power loss with different length of the wavelength. We can calculate just by using the different weight, different group period. Multi-channel, if you put multi-cascade fiber for the 2 long period grating, for 5 long period grating, for 10 long period grating, for 20 long period grating, you can get the unique sharper rejection patterns, rejection band filter. So this is rejection band filter application with the multi-channel filters. Very much useful for the pressure sensor. You can see different see the way different weight is given here, 2.5. So color is showing the different weight. Different weight, we are able to get different power, and this one will tell you that how much pressure has been applied for, and based on different pressure you are able to get different power. So this is one of the another application as a pressure sensor. The pressure sensor based on the how much weight you are using on the room. So not only this, we can calculate the sensitivity of the pressure sensor. So this is the main intention to doing all this. Okay, so transmission loss we can see just by applied the pressure, different pressure. See here, the relative loss is increasing. Okay, so if you know the relative loss, if you know the applied pressure, based on that we can calculate the sensitivity. So here in our case, we got the sensitivity of long period grating at 600 micrometer, which is coming around 5 decibel per kilogram. So you can see how come this applied weight is responsible for the calculating the sensitivity of the long period grating for a specific period, which is around 600 micrometer. So long period grating has a lot of application, especially in the fuel adulteration. It's very much useful. You can see here, this is the laser, this is the fuel has been kept inside. Now the ultra long fiber grating is passing by. Okay, and then output you can calculate, output you can have a look here at the OSHA. Okay, so the ultra long is a ultra long fiber grating. Ultra long means it's going to be more than 100 millimeter. So means more attraction will take place, more coupling will take place with core and fundamental modes and the fuel on the surface of the cladding region. More attraction will take place, more coupling will take place, more transition will take place, and due to that region, how much transition is there, how much interaction will take place this fuel with a long period grating, and much more accuracy we can get, and that accuracy we can see at the OSA. You can see here. So this ultra long period grating has a lot of application, and this application we can use as an external perturbation in terms of the fuel sensor. These are the group what we use. Desi jugaad, we have did that 600 micrometers group. We have taken 1200 micrometer, 1800 micrometer group, 2400 micrometer groups. Okay, and these groups just put it, kept on the surface of the optical fiber, apply the pressure, we can get ultra long fiber bragg grating, and like that we can sense the output. Like groups are like that, you can see here. These are the groups. This is the groups, and this is the how the change of the refractive index will take place with 70 millimeter length. So different range of the groups, or we can say periods, different changing variation of the refractive index inside the optical fiber. The optical spectrum analyzer to detect the spectrum, same thing here. So this is already here. This is the transmission characteristics of long period fiber grating for different percentage of kerosene in petrol. Just by using the long period fiber grating, we use as a sensor fuel adulteration. So as we know that generally in petrol there is a kerosene oil has been mixed. Okay, so how much percentage of kerosene oil has been mixed, we can calculate by using the long period fiber grating. You can see here, this is the wavelength and this is the power. So different color is showing that how much percentage of kerosene oil has been adult inside the petrol. So you can see that this is petrol with 30%. So means higher adulteration is there. So its graph is coming like that. Okay, just we taken the reference with the air. So we see the different percentage of the fuel adulteration. So based on that we can sense the fuel adulteration just by using the long period grating, and just by same systematic arrangement as I showed you previously. Based on that we can get the different adulteration. At least basic idea we can get that this petrol is added with kerosene or not. So this is one of the very good work, and this work has been already published. See, this is a transmission characteristic of long period grating, a single mode fiber, band rejection filter, multi-channel already we discussed, pressure sensor. So this is the sensitivity. Okay, long period fiber grating is very much useful for the refractive index sensor. You can see here this is the long period grating. Long period grating. This is the core region. This is the clad region. Now light is coming from the core region. You can see here, and here what coupling is started. See, now coupling is started. And suppose you put any substrate here, this black region, shaded region. So because this light is hitting the clad region, right? So this substrate will going to be interact with this coupling here. This, so that's why this will be very much sensitive, especially for the sensing purpose. If you're using such type of the fiber bragg grating, long period fiber bragg grating for the sensor as a adulteration of the fuel, adulteration of the milk, just put that substrate on the surface of here. You can see it was the long period fiber bragg grating, and he will be heating here. Coupling will take place, and that coupling information will tell here optical spectrum analyzer, and we can detect that how much adulteration will take place. So of course you put one reference, okay, and then put some substance, and based on that we can predict that how much percentage of the substance is affected or adult. So this is one of the application of fiber bragg grating, just the same phenomena of the coupling phenomena of the core and forward propagating sliding modes. So not only for the sensor purpose, but fiber bragg grating is very much useful for the optical communication. We know that in optical communication we use the so many components. For one of the components which is very famous is the EDFA, rubium dot fiber amplifier. We use that for the amplify the signal. Okay, so EDFA we can use the bragg grating, fiber bragg grating, long period fiber bragg grating for gain equalizer. I will tell you how. So this is one of the very good application of the fiber break grating in the telecommunication field. Okay, dispersion compensation, another issue which is take place in the optical fiber communication, the dispersion compensation. We can avoid such problem just by using the long period grating. Add drop demultiplexer in WDM. This is another issue which will take place in the telecommunication. Fiber laser. We'll see how come such are very much going to be overcome such problems just by using the long period grating. Of course, is very much useful for the sensing technology, strain sensor, temperature sensor, chemical sensor, and so many. So first we'll see that how come gain equalization will take place in EDFA. See here everyone. So this is the EDFA. This is the EDFA gain. How take place the gain in the telecommunication just by using the EDFA, iridium dot fiber amplifier. So you can see it's not flatter, right? Down then up. It's not flatten. So gain is not flatten. We need the flatten gain. So how to do that? So for that one, you need to be use the long period grating who can make exactly opposite of same output, opposite of same output, and then compensate together, and then you are getting such type of gain flatten EDFA. Okay, so suppose EDFA gain is this. See here everyone, this is the EDFA gain. Okay, which is not flatten, and you want to make flatten like this. What to do? Just by using the long period grating, just get the opposite spectrum like that. Opposite spectrum of this one. Okay, and once get the opposite spectrum of this one, just compensate together, join together, you are able to get a flattened gain by EDFA. So this is one of the very good application of the long period grating in the telecommunication to gain equalization in iridium dot fiber amplifier. See here, dispersion compensation. As you know, the one of the main problem in the telecommunication is the dispersion. See, light signal coming, the original pulse is something very sharper like that. Incident in single mode fiber. After maybe 500 or 1000 kilometer, broaden the pulse because of the dispersion phenomena. Broaden the pulse means loss of the information. So by using the brake grating, we can get the same pulse. See here, recirculating by the chip fiber brake grating. Now we are getting the same pulse whatever is in the original pulse. So this is one of the way to find out the whole the information. Which one has been sent in the beginning, same information you can get the end. There is no effect of the broadened pulsage or loss of the information just by using the fiber brake grating. Another problem which will take place, dispersion compensation. You can see here. So some modes are reaching early, some modes will reach later. Okay, so that's why dispersion will take place, or we can say delay difference will take place. So how to avoid that delay difference? Just we can avoid the delay difference just by making such type of the grating. You can see that grating period is smaller here, grating period is bigger here. So light signal is coming to the bigger grating period, lambda 4 coming and the light which is coming from the smaller period, they both, or we can say they all are reaching at the same time here. There is no delay difference will take place. Okay, this is the one of the very good application of the fiber brake grating, which is known as dispersion compensation. So this is the another application which will take place in the telecommunication, known as the dispersion compensation. Okay, of course, sensing technology is very much useful in the fiber brake grating because of the unique property, non-electrical method of operation, explosion proof, no cross connect, no short circuit, very small size, flexible. Okay, this is the property of the fiber brake grating. This is the region. It's very much useful for the sensing technology. You can see here how the sensing will take place. See, this is the input spectrum which is coming inside the fiber brake grating, and this is the reflected spectrum. This is the reflected, and this is the induced shift, which is known as lambda b. See, this is the source, light is coming here, and this is the grating reflected back. We can monitor here. So this reflectance, if you get some shift, wavelength shift, this wavelength shift with lambda b will tell you the property of the things what we are putting on the surface of the grating, have the sensing property. So this lambda will tell you all the information of the sensing of any material what you are planning to sense just by using the fiber brake grating. So induced shift play an important role here. You can see that how the emission field work as a sensing purpose. Light will to and fro with the total internal reflection law. These are the maybe you put some bacteria here on the surface of the optical fiber. You can see it, and light is going to penetrate, or we can say evanescent field will hit them and then come back, and then you can get at the output. So this is the fiber optic immunosensor, especially useful for the optical sensor, or you can say optical biosensor. The systematic setup of the portable evanescent wave optical fiber biosensor. So we can conclude that mechanically enclosed gratings have many advantages. Applicable to any type of the fiber, is inexpensive, does not require costly laser, very flexible, can be operated at any temperature, reversible, flexible, easy to fabricate, periods of few millimeter. So this is the way we can say that the long period grating or ultra long period grating have a lot of application, not only in terms of the sensing, but also in terms of the telecommunication. So these are, we can conclude with different period ratings, that long period ratings 600 micrometer, peak strength without the loss of 7 decibel, ultra long period fiber grating periods 1200 micrometer and 1800 micrometer. The resonance shift is around 20 nanometers. You can see that 600 micrometer and 1200 micrometer have big difference in terms of the sensing purpose. Okay, that's why the ultra long period fiber grating greater periods are more sensitive to the external applied pressure. So generally, if you use the ULPFG, then it will be very much useful, especially for external applied pressure, are very much sensitive and very much accurate you can get if you use the ultra long period fiber grating around 1200 micrometer to 1800 micrometer. This is very much useful, especially for the external perturbation. Okay. These are the references. These are the publications based on the work what we did. How many publications we got based on the long period fiber grating and the ultra long period fiber grating as a sensor purpose. Thank you very much.
Yeah. So, any question? Vivekanand sir, you can unshare your this one
Yeah, I'm trying.
PPT because your photo is not coming. So, any question from the participant side?
Hello, sir.
Yes.
Actually, sir, my question is related to application. So
Yeah.
suppose there are many applications, sensors, parameter which we want to sense. Suppose physical, gas, and chemical. So how we can decide that we should go for FBG and we should go for LPG or ultra? What is the idea in my mind?
Good. Yeah. Good question. In fact, based on the period, see, we know the fiber grating period is very smaller, and long period grating period is bigger. Ultra long period grating is going to be 1200 micrometer. Okay, so based on the period, we can decide what application we are looking for. As I told you, if you're using the ultra long fiber grating around 1200 micrometer, then it's very much useful for the external perturbation. Means if you are using anything on the surface of that, then you go for the ultra long period fiber grating. And if you are using for virus, which is very smaller, if you want to detect virus, then of course you have to go for the fiber grating, whose periods will also match with the scale of the virus, scale of the antigen, antibacteria. So based on the size, what you are going to detect, you can decide the what grating you are looking for.
Okay. So you mean to say that the grating uh, period should match with the particle or
Substance, yeah.
sub particle of
Yeah, because every particle have different size. Some particle have bigger size. Some particles have, for example, if you are looking for a virus, so virus is smaller than bacteria. So of course, based on the size of the virus and bacteria, we have to choose the grating, and based on that, we can go for the application of that. Virus very difficult to detect by using the long period grating. Ultra long period grating cannot detect the virus. Only we can detect the fiber grating. Okay, so based on the scale, based on the grating, all this keep in mind before going to sense whatever you want to sense the substance.
Sir, one thing also, sir, there is some transmission spectrum we can use. We generally use in LPG,
Yeah,
and in FPG, most of the things we use
correct.
reflectivity and
Yeah,
reflective spectrum.
yeah, yeah.
So all the is there all the work we have, there is no reflectivity in case of LPG,
Again,
or
didn't get you.
there is no reflectivity concept, no, in
In
LPG.
long period grating,
Yes.
99.99% transmittance is there, but we cannot say there is no reflectivity 100%. Of course, some reflectivities will be there, but we ignore that. Generally, we go for the majority.
In case of sir FBG, most of the things go for shift. We measure shift in fiber brag wavelength, and uh, we calculate the how much shift is we are getting related to the external perturbation. But in case of the LPG, so what is the principle behind of sensing? It's a intensity or the peak which we are getting in transmittance spectrum, or
Uh,
there is no concept of any shift.
No, of course, these things affect, that if you're going for long period grating, then, the coupling play an important role. How strong is the coupling with core and cladding mode? This is play an important thing if you're
Okay.
going for the long period grating. Okay,
So
so we
there
can,
there must be shift. There must be shift in the central wavelength in LPG also.
yes, correct, you're right. Should
But
be shift, supposed to be shift there with 1500 nanometer, the central wavelength. This is one of the factor if you're going for the long period grating. But if you're going for the fiber period grating, reflectivity, how much strong reflectivity is there, that one will tell you how much accuracy of your sensing substance is there. So of course, reflectivity and transmittance in fiber period grating and long period grating play an important role for the understanding the part of the sensitivity of the any sensing of the substance.
okay, sir. So, sir, related to fabrication method. So, we have studied point by point method. So,
Correct.
we cannot use a
Yeah, yeah. So, but we
only
cannot do.
point by point method.
No, so many methods are there. This is one of the methods because point by point method is very precise method. Because movement is supposed to be very precise. We use the motor which will move in micrometer, in nanometer, in scale. This is very sensitive, in fact, the point by point method. We can go for that. Actually, one of my student did point by point method just by using the electric arc. Just by that electric current produced by the bike, and just putting near the bike the optical fiber, and the electric arc has been incident on the specific portion of the clad region, and then this is not the issue. Second, the problem is that how you going to be measure the micrometer scale, because that one supposed to be specific motor supposed to be there who can move very specific micrometer in scale, then another arc will incident in another micrometer, then periodic variation will take place. So it can do it, of course, by taking the proper precautions. Point technique is also very good technology. Diffuse the the silica material from the core region of the optical fiber.
Okay. Okay, sir. During the fabrication, we strip the fiber, we remove the coating, and then we will do the
Correct. We have the splicer machine. Of course, so many steps are there. First, to remove the jacket, then remove the cladding. Okay. Then bring the core together inside the splicer machine, and then
how the
electrical
sir
PNC.
cladding, how the cladding can be removed, sir. It is also
Yeah,
glass.
we have some instruments, some scissors are there who can remove the cladding also.
Okay, so we can reach till 10 microns from top, no?
Yes, we have
Till the core.
here in Alliance University, we have such of the facility. If you are interested, you can come here and you can interact
Okay.
with my PhD students. They can let you know that how come remove the jacket, how come remove the clad, and how can make the strip together. This is technologies are there step by step to follow that. We can do it.
Okay, sir. Thank you, sir.
So any other question? Okay, then one question I will ask. Actually, Vivekanand sir,
Yes,
you worked on the fiber bracketting. So fiber bracketing for adulteration of the kerosene.
correct.
Yeah. So you have removed the uh, clad part, and that one you have dipped that fiber bracketing. You dipped in the kerosene,
Correct.
which was having adulterated one.
Correct. Actually, we use
Is
the
it?
vacuum chamber for that. If you put this adulterated material in the vacuum chamber, it will much more appropriate result we can get. So first we make the vacuum chamber, and then any material if you want to put, then because if you put the vacuum chamber, there is no any other scattering or absorption will take place. So this is the way. So then we have to remove the cladding, and then we insert inside this adulter material, whatever it is, maybe the fuel irritation or milk irritation. Some of my students did on the milk irritation also, same phenomena, and then they got the transmittance of the long thread grating, and then we can get the how much adulter it is based on different percentage of the adulteration.
But my problem is when the grating length is there, na, the grating
Hmm.
length itself is a very small actually. It is in the form of the mm. So
Hmm.
if we are removing the cladding, the total grating length is in mm. So in the fiber is a lengthy fiber, but in the fiber when we are writing the grating, it is of very small milli mm.
So when you are
Mm.
going for the long period grating, right?
No, normal,
Go for the
normal
ultra, no, normal grating, no, not grating.
grating only.
So grating generally you go for 1200 micrometer, ultra long, then much more better. Compare of the long period grating. If you go for the ultra long, then more interaction will take place with the cladding modes and on the surface of the material what you are using. So if you're going more than 1200 micrometer, then it will be accuracy will be more compared of the long period grating.
Okay, it means that as per your suggestion, length grating length should be very higher.
Yes, should be ultra long, UL, ultra long fiber bracket. Then will be much more appropriate. What we did is by using the ultra long only, we did not go for the long period rate.
Getting fiber is a challenge actually because we are not fabricating. So when
Yeah,
we are
it's
getting,
different.
it is taking long time actually for the. This is the
For our
challenge.
case, we use the etched technology. Just the etching the optical fiber in the HF, hydrogen fluoride, and based on the etching, it's going to be very much sensitive. Based on the how much time you are going to etch, how much concentration of HF is there. Based on that, if you etching, and then if you using such fiber inside the the adulter material, then this one also very good specific for the sensing purpose. So you can check for such method also.
So you are not going for any packaging or any to give the mechanical strength because and once you have removed the clad, you can't use that fiber brag grating for any pressure sensor or any other sensor. Correct? It will be
Here,
used for that.
it depends upon reversible or non-reversible. What step grating we are going to make. If you are using the non-reversible, for example, some of my group they have fabricate the reversible sensor. So just they use the materials and sense, and after cleaning they use as the same fiber. No reverse, no materials will be inside. So depend upon which type material, which type sensor we are going to use. Reversible fiber we are going to make reversible or non-reversible. Based on that you can decide your research.
Okay. Thank you. Thank you very much for the elaborate discussion and so many questions you have taken. Really, I'm very much thankful to you. And in such a short period of notice, you are ready to give the talk. This is also
Always,
very
always,
admirable.
always, ma'am.
Thank you so much.
Anytime if you want my
Thank you so
experience
much.
and knowledge, I will be available to share the experience and knowledge with audience and the colleagues, faculty.
So, okay, anyone from the audience side, if you want to collaborate, you can collaborate. Vivekanand sir is very cordial in nature for collaboration. I think so. Correct, sir?
Ma'am, of course, we like to work because research is not individual. I think research is a collaborative work. Research if you're doing in the group, then you will get so much new ideas.
Yes,
So
yes, yes.
alone you cannot do. As you know that you are also working in so many group, no? So your work is
Yeah, so
also
many.
so standard work you are doing with your PhD students and with colleagues. So you know well. So collaboration is very much important. Maybe
We are
sometime I will
learning.
learn
Day
from
by
some
day, we
new
are learning.
researchers.
We all are learning.
Yes, ma'am. Of course, sometimes we got to know something new things from our research students. So
Yes,
always
yes.
step interaction is very important.
Very nice. Okay, audience. And one notification for all the audience. Today, actually, morning talk was from Dr. Kamrul Hassan from Malaysia. So he is, I think, sir, you know him. He is from Malaysia,
How much
UKM
university?
University.
Yeah,
UKM
yeah.
University.
University ke Mangsar, Malaysia. Yeah, I know that.
Yes, yes.
He's very senior professor. Yeah,
He is very senior professor.
I know him.
Yeah. Under him, PDF is also possible. He told.
With him, yeah. I think so many PDFs working under him.
Yes, yes. So he is, he, as per Malaysian time, 2:30, he told he will be ready. Means 12 o'clock, na?
So two hour and 30 minute back.
It means hour is 12 o'clock,
Ah,
he
12.
told. So, audience, can you join by 12 o'clock again, or else I have to change the speaker because he is not having time. So, from audience side, anybody, any reaction? This is what I want to know. Anyway, I will post in the group
Maybe
also.
they can message
Okay,
and let you know
I can
in the group.
message. Yeah,
Yeah.
yeah. So, Asha madam, now I think all the
Yes, ma'am.
questions are answered. So, formal way, you can
Okay.
wind up this
Yes,
session.
yes, ma'am. Sure. On behalf of the Oxford College of Engineering, I extend heartfelt appreciation to Dr. Vivekanand Mishra for graciously accepting our invitation and delivering an outstanding session. His presence today has been invaluable, and we are truly grateful to you, sir. Dr. Mishra's insightful discussion on long and ultra long period optical fiber grating and its application was exceptional, addressing all queries from the participants. We trust that our audience will utilize this knowledge imparted by him effectively. A big thank you to all participants for your enthusiastic engagement. Uh, Thank you all. Thank you for joining, and thank you, sir.
Thank you, sir. Thank you so much. In future also, we will collaborate.
Sure. Always available.
Thank you. Thank you. Asha madam, hello.
Yes, yes, ma'am.
So next speaker, he is from Malaysia. So he told he can take by 12.
Okay.
So what to say?
Can we post this message here in the chat box?
Yeah. Hmm?
Yeah, I'm typing the message.
Otherwise, if it is because participant, I don't know, they will notice or not because our usual time is 2 o'clock. Then I will request any other. He's telling Malaysian time 2:30 p.m. It means
Okay.
12 o'clock. Now it is 11.
11:15 only, 11:20.
Yes. So 12 o'clock. So let them be like this.
Okay.
You will be there 12 o'clock.
Yes, ma'am.
Hmm?
Yeah.
Okay. My class is there. I will go and come back.
Okay.
Hmm. Okay. Then you
I
paste the
just,
message
yeah,
hmm, in the chat box
yeah,
and also in the group also. By 12 o'clock he will join.
yeah.
So I am announcing everyone, those who are listening to me, that he will join by India time 12 o'clock because he's a very good speaker. So I don't want to cancel him. Just now I confirm. Asa madam, do you have his bio data?
I think we have it.
Okay, so by 12 o'clock. Okay. Hmm.
Yes.
Okay.